I hope it started. Okay. So, welcome to the second lecture of this Frobenius singularities. And today we're going to look at integral closure and tight closure. Uh, right, okay. So let's go with that. So this is sorry, what happened? So you can all see my screen, right?
Yes.
If
Yeah.
it's not visible or if
Yeah, it's
or
visible.
whatever, yeah. Just tell me if there are any issues.
Yeah, sure.
So yeah. Okay. So first, uh, quick recap of integral closure. Uh, so we are not going to be focusing on this because our priority is on the tight closure. But to understand tight closure better, it's we need this concept. We need to revise the concept of integral closure. And I think most of us would have already seen the definition of tight closure sometime before, but it may have looked a bit unintuitive. So hopefully this seminar will clarify or maybe give an intuition of why the definition of tight closure makes sense. So definition of the integral closure. So let I in R be an ideal. Of course, R is Noetherian in our setting. And so an element X in R is said to be integral over I if there exists some n greater than 0 and ij belonging to jth power of I such that x power n plus I1 x power n minus 1 dot plus in equal to 0. So such an element is said to be integral over I, and the integral closure of I, integral closure I bar of I is defined as the set of all elements x in R such that x is integral over I. Now, this is a proposition which is common in commutative algebra textbook, which is that this is actually an ideal and I is contained in I bar, which is contained in radical of I. This is also easy to check. And the second property is that the closure of I bar is I bar itself. That is, this operation is a closure operation. It's idempotent. Then some properties are this belongs to I bar if and only if x plus P is integral. So X plus P belongs to I R by P bar for all P in min R, which means if you can if you can say that this element's image in R mod P is integral over I bar for all primes P, minimal primes P, then X must be integral over I. And I bar R reduced is I R reduced the whole bar, meaning where R reduced is just R modulo radical of 0. So this means that the image of the integral closure of the image of I in the reduced ring is actually the extension of the integral closure of I. And the property is if W is a multiplicative set in R, then I bar RW is I RW bar. So yeah, there is a so this is a sort of stronger statement. There's a weaker statement, which is that which is the persistence property. If P from R to S is a ring map, then P of I closure S is contained in P of IS closure. So, oh, sorry. Could I go back to Zoom? Who? Where do I see people who I should admit? Okay, so
Go to the
okay.
participants link.
Participants, okay, admit.
Maybe you
Okay.
can make somebody else like
Oh, okay.
K7 as co-host so they can do
Yeah.
this job.
Okay, Kason, can I make you the co-host?
Yeah. Go ahead.
Okay. It's I don't know. It's okay. Okay. So this is called the persistence property. If that is, if phi is a ring map, then the elements in the integral closure sits inside the integral closure of the extension. But if W is a multiplicative set, then not just the inclusion, we have the equality. And finally, this is a sort of equivalence criterion. X belongs to integral closure if and only if there exists some n greater than 0 such that x power n plus r belongs to I power r for all r greater than or equal to 1. So I guess this is, it's a bit like Bryan-Kunz-Skoda theorem. Maybe I should talk about that in the next session. Yeah, but okay. So this is much weaker. Bryan-Kunz-Skoda's stronger statement. Okay. So I'm not going to prove these results. Proving it will take some time, and it's a digression. But So we want to focus more on the tight closure. So now, if we look at this definition of this integral closure, we can see that here we are considering elements in the powers of I. Now, a natural question might be to ask, what if we replace this power by something like Frobenius power? Of course, the Frobenius power, I power p, is contained in I power p. So the elements that we sort of get as this, which satisfy monic polynomials of this form, we expect them to be contained in I bar. Right? So what I'm trying to say is, instead of in this definition, keep everything else the same, but change this ij to be something like the Frobenius power j. Then whatever elements that satisfy this integral over some property, those elements must be contained in I bar. So if we denote that by some I tilde, then I tilde is contained in I bar. Of course, we expect them to be contained in I bar. So this is, and again, we have to check that whether it is closed, whether it's the operation is idempotent, so that we can talk about it as a closure operation and all that. So that is one intuitive way of thinking about it, but it doesn't work as in that fashion, because here, if you look at this, j can be any integer, but the Frobenius powers are powers of p, so they are not any integer. They must be some p power e, right? So this sort of equation may not work for our need. So there's an alternate criterion regarding the integral closure of ideals. And this is okay. So before that, a notation, which is R0, R0. It is just the set of all, just R minus union of all P, where P is in min R. So
Abhinav.
yeah.
So there in that above definition, ij belongs to a to the j. So
Yes.
some of those ij's can be 0, right?
Some of those ij's, yeah, could be 0. Yeah, sure.
Yeah. So you can still consider those j's to be p to the e's, which are non-zero, on-zero entries, and other entries can be 0, and can still make sense of the I tilde to be contained inside I closure. Right?
Sure. So that was the question I was going to ask. I just thought about it today. I don't know if this definition session or so that
Yeah.
so
All right. Yeah.
the definition of tight closure is it can be found to be intuitive with regards to the next proposition that I will talk about regarding the integral closure. But I thought about like why we couldn't extend this definition itself instead of going to an equivalent criterion of integral closure and then sort of build upon it. So maybe I'll just write it as a question and we'll discuss it in the next session. Okay. After thinking about it the coming week. So the notation, this is R0 is going to be the set of all elements which are not in, that is R0 is the set of all elements of R, set of all elements of R not in any minimal prime of R. So now the proposition is again I in R be an ideal. Mhm. Then X in R be an element. Then X belongs to I bar if and only if there exists some C in R naught such that C x power n belongs to I power n for all n large. So this proposition may take a bit of time to prove, so I'm not going to go into this. If you want, we can discuss this in the next session also. Just that it will be a bit more involved, and I want to go to the tight closure part, so we'll postpone the proof or maybe omit this. It's there in the notes, so if you have some queries, you can also refer to those. Yeah. So this gives us an alternate description of the integral closure of an ideal. Now, once we have seen this proposition, the definition of tight closure will become very intuitive. So this is the tight closure. Again, let I be in R be an ideal. Remember, ring R is Noetherian and of characteristic P. And X in R be an element. Then we say that X belongs to the tight closure of I if there exists some C in R naught such that C x power q belongs to the Frobenius power for all q large enough. And note that q is p power e. So as before, we are labeling q as the prime power. So this definition is very similar to the integral closure, only that instead of looking at the ordinary powers of I, we are looking at the Frobenius powers of I. So one again, so let the continuation of the definition is denote denote the tight closure of I by I star, and we say that I is tightly closed if I is equal to I star. So yes. Right. So as an example, of course, we want an example which is non-trivial, and consider this F3 xy modulo x square minus y cube. And let I be this principal ideal y. Now, what is I star. So let's think about this. Um, a priori, we know that I is contained in I star, and that is by the definition here. If we look at this, uh, we could very well take C to be 1, and if we take C equal to 1, then any if Q belongs to if X belongs to I, then X power Q will belong to the Frobenius power. So this condition is satisfied. Therefore, this I is contained in I star. But our question is whether there are other elements outside I, which are also contained in I star. The claim is also Y belongs to X belongs to I star, and we can see why. So to see this, take C to be X, and note that X belongs to R naught because this element R itself is a domain. This x square minus y cube is irreducible in F3 of x comma y. Therefore, R is a domain. Therefore, R naught is just the non-zero elements of R. So we can take C to be X, and so the prime powers Q is going to be 3 power E for E greater than or equal to 0 because P is 3 here. So now consider X dot. So we are considering what? C dot, then C dot X to the power Q is X times X power 3 power E, which is going to be X is going to be X power 3 power E plus 1. And of course, X power 3 power E plus 1 is even, right? So we can write this as X square times 3 power E plus 1 divided by 2. And this is because we are, okay, maybe I should, sorry. Let me just make a small change here. So this is capital X, capital Y. To differentiate it from, let X be X bar, Y be Y bar. And then the rest of the notations will still carry over. So, yeah. So this is X square is going to be Y cube because of this quotient, the polynomial. Y cube power 3 power E plus 1 divided by 2. And this is going to be Y power 3 power E times Y power 3 power E plus 3 the whole divided by 2. So what are we doing here? Because this is 3 times this element, it's just this element plus half of that, whatever. So but this belongs to I power 3 power E. So that is because I is a principal ideal. So since I is Y, I power Q is just the ideal defined by the qth power of Y, as we saw before in the last session. So this belongs to I power 3 power E. And so maybe I should just erase this. So, and this is for all e greater than or equal to 0. Yeah. Then, okay, maybe I'll write it here. So for all greater than or equal to 0, this is true. Hence, x belongs to I star. And, of course, um, we will see later that I star. No, not maybe we'll see later. Anyway, it's by the definition of the tight closure, we can immediately. I'll write it again sometime down, but I power q is contained in IQ, and so I star is contained in I bar, which is contained in radical of I. Therefore, since I star is contained in I bar, contained in radical of I, and radical of I is going to be contained in the maximal ideal XYR. Of course, since x comma y is contained in this, hence I star is equal to x comma y. So this is the tight closure of the ideal I, and we can clearly see that this is not equal to I.
Abhiram,
So this is, yeah.
when you wrote the characterization for the element B in the I closure, that is
Hmm.
nothing but there exists some C in R naught such that
Not, yeah.
times that proposition. Yeah.
Yeah.
So there you mentioned for every large enough n. So large enough n means like eventually it will be satisfying for every power of n, or
Uh,
for bigger numbers like 5, and then it may happen for 10, it may happen for 14.
mm, okay, maybe this proposition is for infinitely
Uh,
many
okay.
n. So
So
yeah,
then,
okay. So
okay.
I see that. Yeah, okay, okay. Huh. So if it was like all n greater than large enough, then this may not, the tight closure may not correspond to that proposition. But yeah, so if we the proposition is in fact this one.
Okay.
So with this proposition, then if for the
Yeah,
tight closure element, they are
yeah, the
contained in
element.
interclosure.
Yeah, yeah.
Yeah,
Okay.
yeah. Okay. So anyway,
So I have a
yeah,
question.
yeah.
So, so suppose the ideal is tightly closed, whatever
Hmm,
the
hmm,
definition is. Is it also
hmm.
integrally closed?
No.
Yeah, it doesn't feel like that, but maybe
Huh.
can you give an example?
Okay. So example, I can't think about one immediately, but so
Maybe then, yeah, you can give after talk while you make notes, etc.
yeah. Uh,
Yeah.
but I can mention something, which is that there are rings where every ideal is tightly closed. So those rings are called weakly F regular rings. But um, even in those rings, not all ideals have to be integrally closed.
Mm.
So what are some ideals which are not necessarily integrally closed? So uh, can you think about some in the polynomial ring itself, right? Of course. Yeah. Here's your example. Um, so mm, let R be the polynomial ring FP x1 to xn and not xn. I just want two variables s comma t. Yeah, S comma T. I be the ideal S square comma T square would work, right? Yeah. Okay. So of course, P is greater than equal to 3, some condition. Okay. Then I bar is not equal to I because yes, T belongs to I bar, but not in I. So maybe it's easy to check. So yes, T the whole square minus S square T square is 0. So this is an integral equation, right? You just replace this with X. Yeah, okay. So yes, T belongs to this, but R is, we will see this in the next few lectures. R is regular, hence it is hence it is weakly F regular. So all ideals of R are tightly closed. That is, I star is equal to I. So there you have. Hence, I star is not equal to I. Is this okay? So modulo this fact that regular rings are weakly F regular. Weakly F regular, it's by definition, all ideals are tightly closed. So that is one proposition which we'll see later. But modulo this fact, I think this is one very common example. It occurs everywhere. This is even true for regular rings. So there is no hope for most of the rings, except if you're considering a field or a PID.
Also, in the
Hmm.
previous example, what is the
Hmm.
tight closure for the ideal X?
Tight closure for the ideal X.
Yeah.
That's a good question. Maybe I'll
You
write it
want to
as an
leave that
exercise.
next? Okay. Yeah.
Yeah. Exercise. What is X? So the in this proposition, the tight closure of I was, we were able to work it out because the characteristic of this ring is 3. But I don't know if it will work the same for X. Yeah, that's something to check. And okay, so now uh, some properties of tight closure. So let I in R be an ideal, then 1. I star is an ideal. I star, the whole star is okay. I star is an ideal, and I is contained in I star, which is contained in I bar, which is contained in radical of I, and the third is maybe I'll then next is if I is contained in J, then I star is contained in J star, and the third is I star, the whole star is I star, that is a closure operation. That's why it's called tight closure, not tight operation. Tight operation would be a very bad name, but okay. So first is we have to check whether it's an ideal, and so if x comma y belongs to I star, then x, so there exists c comma d in R naught such that c x power q belongs to I q and d y power q belongs to IQ for all q large enough. Now, so here we want to make a distinction. Let q1, q2 be such that c x power q1, not q1, c x power q belongs to IQ, dy power q belongs to IQ for all, maybe, for all q greater than or equal to q1, and dy power q prime belongs to IQ prime for all q prime greater than or equal to q2. So once we have this q1 and q2, now look at then CD, the whole power, the whole xy times q prime, right? So this belongs to q prime for all q prime greater than or equal to maybe not. So I'll just write q here. This q for all q greater than or equal to q1, q2, and that can be seen because if it passes either of these q or q2, then x plus y the whole power q should, when you expand it in binomial coefficient, okay, no. Oh, this is this powers, right? Yeah, x plus y the whole power q is x power q plus y power q. Anyway, so this is just max q1, q2. This is Frobenius morphism anyway. And CD also belongs to R naught because C is not contained in any of the minimal prime, D is not contained in any of the minimal prime. By the property of primes, the product is also not contained in the minimal prime, therefore, yeah. Actually R naught is a multiplicative set, and yeah, so CD is in R naught, hence x plus y belongs to IQ. Similarly, if R belongs to R, X belongs to I star, then Rx belongs to I star, since if C x power q belongs to IQ for all q large enough, then C r power q x power q belongs to IQ for all q large enough, hence Rx belongs to I star. So I star is an ideal. Okay. So the other part is I star is contained in I star is contained in I bar. So suppose X belongs to I star, then there exists C greater than C in R naught such that C x power Q belongs to IQ for all Q large enough. Hence, C x power Q belongs to I power Q for all Q for all infinitely many Q greater than 0. Hence, X belongs to I bar by proposition. And yeah, it is, yeah, that's it. And it is easy to check. If I is contained in J, then I star is contained in J star, or that I is contained in I star. So now we'll move to the third part. Note that I is contained in I star, hence I star is contained in I star the whole star. So now let X belongs to I star, X belong to I star the whole star. Then there exists some C in R naught such that C x power Q belongs to I star Q for all Q large enough. So now consider the generators of I star. These are going to be finitely generated because our ring is Noetherian. There exists Ci belonging to R naught such that Ci f I power Q belongs to IQ for all Q large enough. And because these are finitely many elements, we can choose Q such that the Ci Fi power Q, of course, I don't know how to explain this. Okay, so now define D to be C times C1 times C2 dot CT. These are all elements in R naught, therefore the product is also in R naught. And now okay, so D x power Q. Okay, suppose suppose our x power Q. We've so we have that C x power Q is in the qth Frobenius power of I star, right? So this must be of the form summation Ri Fi power Q for some So this is from I from 1 to T, where R is in R. Then D times x power q is what? C1 dot 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 Ct times C x power q, which is C1 times Ct of summation Ri Fi power q, I from 1 to T. Note that C1 dot 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 Ct Ri Fi power q is just C1 Ci hat, meaning I'm omitting that Ci, times C times Ri Ci Fi power q, which is now inside I power q, because this particular quantity Ci Fi power q is in this I power q. For all 1 less than or equal to I less than or equal to T, hence d x power q belongs to IQ for all q greater than 0, for all q large enough. Hence, x belongs to I star. That is I star whole star is equal to I star. This is a closure operation. Okay. So now some proposition. Again, let I in R be an ideal. Then number 1 is that radical of zeros contained in I star, and x belongs to I star if and only if x plus p belongs to I plus p the whole star times r by p, meaning for all minimal primes p of r. And the third part is if r is reduced or site I is 0, then x belongs to I star if and only if there exists C in R naught such that C x power q belongs to IQ for all q greater than or equal to 0, greater than or equal to 1. Yeah. So what the third part of this proposition is saying is that instead of looking at the large enough values, it gives you a stronger statement that Ix belongs to I star if and only if all the powers of there exists C in R naught is that C x power q belongs to the Frobenius power of I for all q, not just large enough q. Okay, so yeah, now proof. The radical part is clear. Okay, so I forgot on that. And if I is principal ideal, then I star is actually equal to I closure. Yeah. Okay. So now we will look at the proof. So proof of one. It's so let x belong to radical of 0, then x power n is 0 for some n greater than 0. Hence, taking c equal to 1, we see that c x power q belongs to the Frobenius power of q for all q large enough. Hence, x belongs to a star. So that is the inclusion. And now suppose I is principal, then the Frobenius power is just the normal power of I. Hence, if hence x belongs to I, okay, with this observation, let x belong to I, some I bar. Then there exists C in R naught such that C x power n belong to I power n for all n large enough. Hence, C x power q belongs to IQ, which is just I power q for all q large enough. Hence, x belongs to I star. So, thus, I star is I. So the next proposition is so we want to show that x belongs to I star if and only if the image of x belongs to the tight closure of I in R modulo P for all minimal primes. One inclusion is clear because if x belongs to I star, then there exists C in R naught such that C x power q belongs to the Frobenius power of I for all q large enough, and C belongs to R mod P 0 because C is not C is not C is does not belong to the union of P in min R. Right. So hence C not C. Hence X bar, which I'm using it as the image. This belongs to maybe bar is not a good idea. So X plus P belongs to I plus P's closure because of this property again. For all P in min R. Okay. So that is one direction. Now suppose X in R is such that x plus p belongs to I plus p's tight closure for all p in min R. And so there exists, hence, okay, let min R is the set P1 through PS. And let Xi be the image of X in R modulo Pi. So we want a way to track the image of the element X inside these quotient rings. So we'll call that Xi. And by definition, there exists Ci in R modulo Pi 0, which is just R modulo Pi minus the set 0, because R modulo Pi, this is an integral domain. Therefore, the minimal prime is just the 0 ideal there, such that Ci xi power q belongs to I power q for all q large enough. Of course, let this thing and I be the image of I in R mod Pi. Okay, so but Ci is an element in R modulo Pi. We want a lift of that element which is outside every other minimal prime. So which we can do by prime avoidance. So what I'm trying to say is we can choose a lift of Ci in R lift of Ci in R lift Ci prime such that Ci prime belongs to R naught. This is by prime avoidance because our Ci is in R mod Pi minus 0. So Ci is definitely not in the prime ideal Pi. And while we are choosing an element which is in the class of this Ci, we can so this is because um, we can consider Ci plus P the set, and consider the set Ci plus so not the set Ci, we are considering the inverse image, which is inverse image of Ci in R mod Pi, and this set is not in union of P. The set is not in actually not in any of Pi. Hence, it is not in the union union Pi I from 1 to S. I hope this is clear. If it's not, we can talk about this again. What I'm trying to say is that the inverse image of this element Ci is not in any of the primes Pi. So what prime avoidance says is that if an ideal I is not in it's not in any of the Pi, any of the primes, it is also not in the union of primes. So yeah, we can choose a lift such that Ci is in R naught. Okay, so hence Ci prime times x power q, it belongs to I power q plus pi, because uh, this property holds in the image uh, for all q large enough. And now choose pi. Yeah, choose ti in all the minimal primes of R except pi. So we are just choosing elements Ti, which are in all the minimal primes of R except in Pi. That is, Ti belongs to R minus Pi for all 1 less than or equal to I less than or equal to S. Now, we define D to be summation Ti Ci, I from 1 to S, and then dx power q is, it belongs to iq plus summation ti pi, because d is multiplication of ti and ci, and so yeah, it belongs to I power q and this summation, and this is contained in iq plus the product, because since ti pi is contained in the product pi, I from 1 to S, and what is this product? The product of the primes is just the radical of 0, because pi's are the minimal primes. So this is contained in qth power of I plus the radical of 0. So now we have some d says that dx power q is contained in I power q plus the radical of 0. And now you choose some q naught such that the radical of 0 power q naught is 0, because this is the nil radical, and this nil radical is also finitely generated. So by choosing the q naught large enough, we can assure that this is 0, q naught power 0. Then this particular element C should be okay. So now d power q naught and x power q naught, it belongs to I power q naught, because for all q large enough, q naught large enough, Hence, X belongs to I star. This is a bit involved and kind of very technical. Yeah. So,
Abhiram, can you
yeah,
go to the part where you did the prime avoidance?
yeah. Which one?
So,
This one?
yeah. So the bracketed part. So you wrote it like
Hmm.
this because we can consider the set which is the inverse image of Ci in Rp. So that
Hmm.
is, you take the fiber of one particular Ci, and then
Yes.
you consider that set, and that set is not contained
Yes.
in any of the PA is what you claim.
Yeah.
So why that is true? Why that's okay? It is not contained in PA. Why it is not contained in any other?
It is not contained. Uh, okay. So if we consider the element Ci, which is a non-zero element in R mod Pi,
Yeah.
and um, so there are only finitely many primes here, right? In R,
Yes.
and while if we can maybe do this by induction, say, if you pull an element in this, if you look at an element in this fiber, and
Mm.
suppose it is contained in some P2,
Yeah.
and then uh, suppose it is contained in P2, then we can okay, we are so um, yeah, we will just first look at P1, say. So the C1 is in R mod P1 minus 0, and we are looking at uh, the inverse image of the C1. And that set is sort of yeah, that no matter what lift that you choose, it's not in P1. Suppose it is in P2, then that okay, wait. I didn't. What about, sorry, maybe okay, look at this ideal of any of the element that you chose. Look at the ideal of the element that you chose, uh, which is uh, so the element Ci will generate height 1 ideal in R mod Pi, right?
Mm.
I
Yeah.
mean by Krull's theorem.
Yeah.
Okay, so this element Ci will generate height 1 ideal, and once you look at the pullback of this ideal, uh, this ideal, which is again an ideal in R, so that ideal will not be contained in any of the prime ideal Pi. Is that okay?
When you take the pullback of this ideal Ci, it won't be contained inside any of the
Prime ideal,
prime.
because any of the prime ideal Pi.
Mhm. So why that is true? Uh,
Um,
so these are minimal primes, right?
yeah, so they must have height. Uh, yeah, maybe this proposition. Uh, I have not thought about that. So, but yeah, P2 could also be a non zero. It could also have a positive height in R mod P1. Maybe I'll do this the next time. Okay.
Yeah, sure.
Yeah,
This
PIs are minimal, no?
PIs are minimal, but if we look at R mod PI and R mod say P1, and then look at the ideal image of P2 inside R mod P1.
Yeah.
So how okay. So how could you guarantee that uh, the element Ci is the lift that you take is not contained in P2. Let me think about this and I'll get back about this in the next class. Okay, next session.
So
Yeah.
one final thing before we proceed,
Yeah.
like, can we say
Hmm.
like the height is preserved under this lift thing because of any integral property?
No.
Can
Wait, what? No.
uh,
Height? No, we can't say that.
so
There's
it
no
is
integral
true if it
property
is
here.
okay. So it is true when it is integral. Oh, never mind. Yeah. Go ahead.
So in fact, what I'm trying to say is, you could have the minimal primes, say P1, P2 up to PS, but all of those primes have height 0. But if you look at the image of P2 in R mod P1, say, that will have positive height. So yeah, the height could decrease, could also increase.
No. What my question
uh,
was, that ideal you chose, right? That's CI.
yeah,
If you
yeah.
contract back, can we say the height of that ideal is again what?
Oh, no.
Uh,
Again, I told you, right? So you could choose an element in P2. Okay. And look
mm,
at the ideal generated by that element. That will have height 0 in R. But if you
mm,
look at that element in R mod P1, that could still have positive height.
okay.
Right? Unless that element is also contained in P1. If we choose
Mm,
an element in P2 minus P1, say,
yeah. Okay.
right? So yeah.
Okay.
Okay. So let me do this and the third part of this in the next session. We'll stop here. Okay.
Hello.
Yeah.
Abhiram? Yeah,
Yeah.
I need a clarification in the definition of integral closure. So
Yes.
sometimes you are using that, uh, the definition in the sense that proposition is there, right?
Yes.
Where X belongs to I closure if there exists C in R naught such that Cx power n belongs to
Yes.
I power n. Is it for infinitely many or for all
Yes.
n beyond a point? Because we have been using that interchangeably.
So maybe this might help. What this proposition says is C belongs to I bar if and only if there exists C in R naught such that Cx power n belongs to In uh, for all n large enough, if and only if there exists C in R naught such that Cx power n belongs to In for all infinitely many n greater than 0. So this is similar to when we look at the localization property, right? So we say the property is local if that property is that is equivalent, say, for example, flatness. So we say that the R module M is flat if and only if M localized at every prime ideal is flat, and if and only if M localized at every maximal ideal is flat. One of the condition is weaker than the other.
Right.
And here, the infinitely many n greater than 0 looks weaker than this n for all
But
n
that is
large
same,
enough.
okay.
But yeah, this holds.
Okay.
So this is the proposition.
Okay.
So we can use any of these three things interchangeably. Okay.
And I
Yeah.
had one more question. This is from the first lecture.
Yeah.
So we had proved that result, right? Perfect if and only if the Frobenius map is surjective for Noetherian rings.
Yes.
So
Yes.
I think your argument, maybe locally Noetherian is enough. Just if you have time in that argument, we are just
Mm,
using the finiteness
yeah.
of TRP, not essentially any Noetherian property of R. We are using Noetherianness on RP, right?
Of course. Yeah.
So,
Yeah.
like you had a question,
Locally
right?
Noetherian is enough.
So maybe it still holds
Locally
for
Noetherian is,
non-Noetherian rings. Like there was a question below that, right?
it
Whether
might hold true.
yeah, for
Yes,
locally
yes, yes.
Noetherian but
Yeah.
not Noetherian rings. Yeah, I think this.
Yeah, sure. No, my question was a bit more general. So I wanted to see if there are arguments which don't use this Noetherian hypothesis or the Nakayama lemma, and somehow conclude that uh, the surjectivity imply the isomorphism of the Frobenius. Yeah, but
I
yeah.
there
Hmm.
might be actually this result is like there are this certain kind of results like subject to endomorphism of R algebras. They are
Surjective?
endomorphisms of R algebras. Suppose the base ring is here we are having Z algebras, right, in a way. Like Z is
Yes.
so take R algebras where that R algebra is finitely generated.
R
Assume
algebra
that.
is finitely generated. Okay.
Then any surjective endomorphism is actually an isomorphism.
Finitely generated as what? R model or
R
R
algebra.
algebra? R algebra.
R algebra.
Oh, so surjective R algebra endomorphism is actually an isomorphism.
Yes. Suppose A is a finitely generated R algebra, then
Okay.
any surjective endomorphism of A is actually an isomorphism. So that
Is that true for non-Noetherian case also?
yeah, it is assuming finitely generated over the base. Like here, what happens is over Z. I mean, it becomes Noetherian, right?
No, so here it's over FP. I mean, over Z is equivalent to saying that
Over
it's
Z,
over
FP,
FP.
yeah. But both are Noetherian.
Yeah.
So here we are getting that in a
Of
way.
course. Yes. Yeah.
So
So
I think
finitely
this
generated
result
FP algebras are.
can be connected to that in a way. Like, I mean, but yeah, that technique cannot be applied here. I was trying to think of an alternate, but maybe if you look at that proof,
So
maybe there
it's
might be some things, perhaps for an alternate proof. I couldn't get
so
it, but
finite generated R algebra. I think they might again use some the techniques in polynomial algebra. So
yes,
finitely generated polynomial
they
algebra. I
reduced to a
don't
Noetherian case.
see if that will be useful here.
Yeah.
Yeah, I don't see how that will be useful here. But then yeah. So local Noetherian, yeah, of course. That's just an extension of this result.
Okay.
Okay, thank you. Yeah. Okay. So we will fix a time. As Aditya says, we will fix a time sometime later. And yeah, see you next time.
Just one small question. Hello.
Yeah,
Maybe you
sure.
can stop
So
recording now and we can discuss that also.
Okay.
what
Let me
here?
stop the recording. Okay.
Oh,